Good morning. I am Dr. N. Fatima from Sagar Institute of Research and Technology. I am taking active filters using operational amplifiers. Before moving to active filters, I want to discuss the log scale for the drawing of frequency response of active filters. It is required to plot the output voltage with respect to a wide range of frequencies. For plotting of wide range of frequencies, log scales can be used. So see now what is log frequency scale. This is the log frequency scale. On this you can see here it is written 10, next one is 20, next scale is 30, 40, 50 till 100. So on the log scale, the values are written like this: 10, after 10, 20, 30, 40 till 100. But after 100, the value will not be 110. The value will be 200, then 300, 400, 500 till 1000. The next value of this 1000, the next value will be 2000 and not like 1100. The value will be 2000, 300, 3000, 4000 till 10,000. After 10,000, the value will be 1 lakh and so on. So this is the log scale. Now, on the log scale, the decade and octave are also defined. So on the frequency scale, what is decade? Decade is actually a tenfold increase. Like you can see here, this is the 10. Here, the value is 10. See, this value is 10. So if this value is multiplied by 10, that is 10 multiplied by 10, this is equal to 100. Now this, you can see this is the 100. Now from 10 hertz to 100 hertz, this is presenting one decade. Similarly, if the 100 is multiplied by 10, the value will be 1000. So from 100 to 1000, from this 100 to 1000, so this is also defining another decade and so on. The next is the octave. Octave is doubling. Actually, the whatever the frequency value you are taking, if it is multiplied by 2, so this is defining an octave. Like here, if I am taking 10 and if it is multiplied by 2, the value will be 20. So frequency from 10 to 20, this is defining one octave. Similarly, see here, if 500 is taken as a reference and it is multiplied by 2, then the value will be 1000. So from 500 hertz to 1000 hertz, this is defining one octave. So these octave and decades are used in slope of frequency response of filters. Now the introduction of the filter. The filters are the circuits which are capable of passing the signals within a band of frequencies and rejects or attenuates or blocks the signal of frequencies outside of this band. So this property of the filter is also called frequency selectivity or simple frequency selection, or this is also called filtering property. The passive filters and active filters are the two types of filters. The passive filters are built using the components such as resistor, capacitor, and inductors. Whereas in the active filters, the resistor, inductor, and capacitor are used with transistors or operational amplifiers in addition of these components: resistor, capacitor, and inductors. So active filters are mainly used in communication and signal processing circuits. The active filters are also used in wide range of applications, like for the entertainment, for the medical, for the electronics, medical electronics, and many applications are there. Now come to the frequency response of the filter. What is the meaning of this frequency response? The frequency response means the graph is drawn between gain and frequency. The frequency is drawn on x-axis of the graph and gain is drawn on the y-axis of the graph. The gain is written in dB. The gain is equal to 20 log of output voltage divided by input voltage. The gain is drawn on y-axis of the graph and this is written in dB. So the filters are having pass band, stop band, and transition region. The pass band is the range of the frequencies which allow the frequencies to pass. Yeah, you can see this range. This range is showing the pass band. Here the gain of the filter is almost constant. So this band or this range of frequencies is called pass band. Next is a stop band. Stop band is the range of the frequencies that have the most of the attenuation. So see here, this is the stop band. This is the stop band from this region to this region. So this is representing the stop band. Next is the transition region. The transition region is the area where the fall off occurs. So this you can see this fall off occurs here. The output voltage is reducing. So this region is called transition region. The next is the critical frequency. The critical frequency or the cutoff frequency is denoted by FC. This frequency is taken from 3 dB down from the maximum value of the gain. So this value you can see here, this is a 3 dB down value. So this value, this particular frequency is called the cutoff frequency. After this cutoff frequency, the output of the filter start reducing, or you can see the output of filter or the filter start attenuating the signals after this cutoff frequency. Now the types of the filters: low pass filter, high pass filter, band pass filter, band stop filter, band or band reject filter, narrow band filter. Narrow band filter is also called notch filter. Now first I want to take the low pass filter, but I want to show the basic circuits of the low pass filter and high pass filter. So this is the basic circuit of the low pass filter where our resistance and capacitor are connected. The capacitor is connected in the shunt, and the high pass filter, the CR network is using where the capacitor is connected in series. Now this is the circuit diagram of the low pass filter. Active low pass filter, the filter which is having resistor, capacitor, and also operational amplifier. So this circuit diagram is showing the low pass filter. So you can see here the filter network, that is RC network. This RC low pass filter is connected to the positive terminal of the operation amplifier and supply is given to this RC network. RF and R1 consists feedback network and it is connected on the negative terminal. That is, negative feedback is provided with the help of this RF and R1 network. So this diagram is showing the first order low pass filter. These active filters are also called Butterworth filter. This is the name of the scientist who invented this. So the active filters are also called Butterworth filters. This F is showing the critical frequency or cutoff frequency of low pass filter. This is equal to 1 by 2 pi RC, where this R and C are these resistance R and capacitor. Depending on the value of this R and C, the cutoff frequency will be decided. Now, when input voltage is given to this operational amplifier to this low pass filter, if the frequency is going to change, this filter passes the lower frequencies and attenuates the higher frequencies. So see here, the gain of this low pass filter is equal to 1 plus RF upon R1, or you can say R2 upon R1, or 1 plus RF upon R1. Since here this is the input is given to the positive terminal of the op amp, so this is acting as a non-inverting amplifier. So the gain of the non-inverting amplifier is equal to 1 plus RF upon R1. So here also the gain will be 1 plus RF upon R1. The output voltage of the filter is equal to AF upon under root of 1 plus f upon fc, f by fc square, where this AF is the passband gain of the filter, F is the frequency of the input signal, and FC is the cutoff frequency. Now see here, at very low frequencies, when F is very less than cutoff frequency, then output voltage will be equal to approximately equal to AF. If the frequency becomes equal to FC, F equal to AFC, then this value comes under root 2, AF upon under root 2, that is equal to 0.707 of AF, that is 3 dB down of AF. But if the frequency is very higher than the critical frequency, then the output, the AV is equal to V out upon V. So we can see for the lower frequencies, the value is AF, and for the frequency F equal to FC, value is 0.707 EF, and for the frequency more than FC, the AV is equal to, this is equal to very low value. So see, this is the graph of the graph or frequency response of the low pass filter. See, when the frequency is very less than critical frequency, you can see this is the critical frequency which is taken 3 dB down from here. This is 3 dB down. On x-axis frequency is taken, on y-axis gain is taken, and the frequency response is drawn. The whatever the value is coming, the 3 dB down value is taken. So this is equal to this. This gives the cutoff frequency. Now, when f is less than cutoff frequency, the value is approximately AF. That is this much one. So this is the gain value. This is a maximum value of the gain. Now, when the f becomes equal to cutoff frequency, then this the value is 3 dB down, that is 0.707 of AF. And when f is greater than fc, the output voltage start decreasing. So you can see this output voltage start decreasing. Now the slope of this attenuating signals or slope of the stop band, this is equal to minus 20 dB per decade. For a decade, the 20 dB gain reduces. For the reduction in gain, the minus sign is written here. So we can see here the fall down of, or the reduction in value of the output voltage or gain. So the slope is minus 20 dB per decade for the first order low pass filter. So this area is representing the pass band from this frequency to this frequency, that is from 0 hertz to FC hertz cutoff frequency. This is showing the pass band. But after this is showing the stop band. This after cutoff frequency, all the frequencies are attenuating, and this is showing the stop band. Now see here, this is the frequency response of the ideal filter, or you can say the ideal response of the filter, where you can see the on the x-axis f is the frequency, and on the y-axis gain is taken. The gain is drawn with respect to the different values of the frequencies. You can see the gain is constant, and after a cutoff frequency, this fh is representing the cutoff frequency. After this cutoff frequency, the gain is immediately becomes 0, and this is showing the pass band, and after the cutoff frequency, this is showing stop band. But this is the ideal response of the filter, but it never happens practically since the capacitor is using, which is charging and discharging. So because of that reason, we got some slope here instead of this steep cutoff. So this is the practical frequency response of the low pass filter. On the x-axis frequency is present, on y-axis gain is taken, gain is drawn in dB. So see, this is the 0 dB or AF, maximum value of the gain, maximum output voltage, and this is constant. The cutoff frequency is drawn from minus 3 dB. So this is showing the cutoff frequency. So from this frequency to this frequency, this is showing the pass band, and after this is the stop band. So this is the practical response of the low pass filter, where low pass filter, you can see allows the lower frequencies from 0 hertz to cut-off frequency and attenuates the higher frequencies. Now design a non-inverting active low-pass filter circuit that has a gain of 10 at low frequencies and high cutoff frequency or corner frequency of 159 hertz. Assume input resistance is of 10 kilo ohm. So first of all, take the gain, feedback gain AF equal to 1 plus RF upon R1 or R2 upon R1. This is given how much? It is equal to the gain of 10. The 10 is given, the value is given here. So take 1 towards right hand side. So this becomes 9. So R2 upon R1 equal to 9. So R2 equal to 9 times of R1. So if I'm considering the value of R1 equal to 1 kilo ohm, then the value of R2 will be 9 kilo ohm. So, but this is not possible to take the value 9 kilo ohm. So instead of taking 9 kilo ohm, we can take 10 kilo ohm. So R1 value becomes 1 kilo ohm and R2 value becomes 10 kilo ohm, or you can say RF value becomes 10 kilo ohm and R1 becomes 1 kilo ohm. Now gain in the dB, this is how much? 20 log of A. Already gain is already given of 10. So this the value of this A is equal to 10. So I wrote here 10. So the base of this log is 10 and this is also 10. So this becomes 1. So the gain becomes equal to 20 dB for a gain of 10. Now the cutoff frequency formula is 1 by 2 pi RC. The cutoff frequency value is already given. This is 159 hertz and the value of resistance is also given 10 kilo ohms. So here FC is given 159 hertz and value of R is 10 kilo ohm. So we can calculate the value of capacitor here. Apply this formula and calculate the value of capacitor. So this is coming equal to 100 nanofarad. So the value of resistance is 10 kilo ohm and capacitor is 100 nanofarad. So this completes this lecture. Thank you.